All right, hold on.
This lady that was going around different schools about just being, and she. Like,
There we go.
She like went there.
Let me get the display on real quick.
But it was because like our school.
Okay.
So we have to charge it before we leave.
It would help if the laptop was called. Okay, all right. Lecture 25. I thought I would go ahead and just make sure that we're all cognizant that we don't have an exam next week, but we have an exam the Monday after. Okay. So what we're going to be doing is we are on our third lecture on deflections on beams and frames. I am going to be assigning a homework today. That homework is going to be homework 6.2. I think I've mentioned this homework in the past as being a little arduous. It is probably our longest assignment this whole semester. Okay, so I can't really do anything about it just because of the nature of the problems. They do tend to be kind of long. So what we're going to do is that homework's going to be due Wednesday. What I'm going to do today and then Monday, so today we're doing an example that involves multiple moment functions, and then on Monday I'm going to show you some tips and tricks to make virtual work faster. And I'll go ahead and mention, if you've already downloaded Lecture 26 on Blackboard, I might download it again because I've updated it over the past day or so. I added an example to it, sort of an interactive example that we're going to do together to sort of get our head wrapped around what it is that we're doing. But that's going to be our topic on Monday. Wednesday, we're going to look at deflection of frames. And then I'll have a little note about shear deformation, and then that is it for exam 2. So Friday next week we will review, and then we will celebrate the following Monday. Okay? Does that sound good? Okay. All right. Then what we're going to do is let's just go ahead and jump right into it. So let me take my keyboard off here. So just so everybody is clear, we are still doing the same thing. But I think what's going to be relevant or important today is the idea that we're going to be summing integrals as opposed to what we did last time and what you did on your last homework assignment where all we did was just an integral. Today we're going to be summing integrals, okay? And the reason why is because we're going to have a problem where we need multiple moment functions. But I kind of like this problem because it's pretty digestible in terms of what it is that we're trying to do. But we can take this problem and really explore ways of making it more general, ways of making it, I don't want to say more complicated, but with that generality does come a degree of alphabet soup. And you'll see what I mean. Now, what we're going to explore today is piecewise moment functions. Piecewise moment functions for both the real structure and the virtual structure. It's possible that if we're doing what I would say a real world problem, we might have multiple moment functions defining our response. For example, we had looked at, I think, this problem when we first started to introduce the idea last time. And the idea is that if I had a beam like this sort of overhanging beam with triangular loads, distributed loads, what have you, I would need a total of 3 piecewise functions in order to fully define the moment diagram. So for example, if I was saying that my coordinate system was, I don't know, right here, maybe I'll draw that here on the screen. Whoop. So we'll say if my coordinate system, oh, that's bad. Let's do this better. Okay, let's say that, you know, that's the X and Y axis, or something like that. So maybe what I'll do is I'll have, you know, something like a moment function, like a real moment function that's valid from x equals 0 to x equals 12. I'll have a second real moment function that's valid from, I don't know, x equals 12 to x equals what, 32? And then another one that's valid from 32 to 38. Does that make sense? The idea that in order to fully plot this, like if I were graphing this, how many of you took math here have used Desmos? You used Desmos before. So imagine if I was trying to create a plot in Desmos. I'd have to have one equation for this parabola, one equation for this parabola, and one equation for this parabola, right? Bounded in those regions. So the same idea would be true here. Now, I'll go ahead and tell you that if you, there are some tricks to make your life a little easier with this type of problem. We're not going to explore these today. We're going to talk about these tricks on Monday. But one thing that you can do is you can say, I'm just going to use this coordinate system over here, and I'm going to put a whole nother coordinate system over here. And instead of this one, I'll change it to this, okay? In other words, I'll say that my coordinate system, that here's my origin going this way, okay? The reason why, I'll go ahead and give you a little sneak peek. The reason why we would prefer this method as opposed to this one is twofold. The first is that we're going to see, this is a little harder to explain without actually just practicing it, which we'll do on Monday. But the algebra is a lot easier with this approach than it is with this one. But maybe what is a little easier to see is that if we're going to integrate this, if we integrate this, we're going to be integrating from 0 to 6. And integrating with one of your limits being 0 is really easy, right? Because how do you do an integral? Like you evaluate it and then you plug in the top number minus plug in the bottom number. So if you can make that bottom number 0, it makes the integral really easy to do, right? So there are tricks that you can use to make your life a lot easier, and we're going to talk about those tricks on Monday, okay? But for today, I want to look at this problem, okay? So I have a beam deflection here, and I want to determine the vertical deflection and the rotation at point B, okay? So the beam is simply supported, uniformly distributed load, and I want to find the deflection, but the deflection is not at midspan. The deflection is over here at B, okay? We're going to do this using the principle of virtual work, and we're going to assume that the beam's made out of concrete. So we're going to say its E value is 4,000 KSI, and because it's concrete, it's got to be a really big beam in order to get the same stiffness. So we're going to say its I value is 6,000 inches to the fourth. So it's a really big beam made out of concrete. So far, so good? Now, I'll address this point a little bit later. I'm just going to sort of ignore that for right now, but we'll address that later. Now, let me ask you a question. Looking at this beam, let's go back to our discussion of piecewise functions. How many mathematical equations, how many functions am I going to need to fully describe the moment diagram? And if you remember the trick of just sort of cutting a section and then moving your section cut across the beam, how many moment functions are we going to need? Say it again? One. We're only going to need one. Now that's the case for the real moment function, but not the virtual moment function. The virtual moment function is going to be different, okay? And we'll get to that here in a bit, okay? So let's get right to it. Okay. Now let's treat this very generally. Let's do this problem as if we are. Let's do it as if we are sort of naive about the response. So let's just sort of do the whole thing. So let's look at the real structure, okay? And there's a couple things we're going to do. So here's the structure. Okay, we're going to have a reaction here, and we know that this distance is 30 feet. Okay, and we call this point A, point B. Okay. Now, one of the things that we really haven't discussed a lot in here, but I think we kind of need to make some recognition of, is the concept of symmetry. Okay, Up until now, if I asked you to solve for the reactions, how would you do it? You would sum moments at A to get the reaction at B, and then sum verticals to get the reaction at A. Is that really necessary? No. What are the reactions going to be? 18 kips. And how do you do that? You say 1.2 kips per foot over a distance of 30 feet is 36 kips, right? So half and half, right? We don't need to go through that rigmarole every time. And I say this because I want you to recognize a lot of what we've done in here has not exploited symmetry, because I want you to develop those skills for structural analysis. But a lot of times in the real world, symmetry happens. There's a beam going from here to here. I guarantee you, analytically it's symmetric. Simply supported, distributed load. You know, no reason to make the problem harder than it needs to be. So I'll say by symmetry, that's 18. That's 18. All right, is that okay? Hopefully that's simple. Yes?
Is there a reason that we didn't name the roller C?
Oh, no. The reason is I messed up. That is the reason. The reason is that I made a boo-boo. Yeah, but thanks for pointing it out. No, but okay, I'm glad that you brought that up, because I do have a follow-up question that I'm going to ask, which is there a reason I have not labeled B on this structure? Okay. Does B matter? No, it doesn't. So it doesn't really matter. I mean, if you want me to label it, I can, but it doesn't really matter, right? I mean, we do have this point B that is, you know, 10 foot away, but it doesn't really matter, okay? Sound good? Okay, now, when I said naively attack this, what I meant is, okay, we're going to start off by constructing the shear diagram, okay? So we're going to go up from 0 to 18. Then what is it going to look like from end to end? It's going to be linear. See if I can do it like this. Okay. Down to minus 18, then back up to 0. Do I need to do any fancy slope calculations to figure out this distance right here? It's right in the middle, right? That's 15 feet. Okay, so 18 times 15 over 2 is just going to be 9 times 15. 9 times 15, that's 90 and 45, 135, right? So we're going to have plus 135. We're going to have minus 135. And then our moment diagram is going to be like that. 0, 135. I can do better than that. And 0. Okay? Does that make sense? Now, this is a really, really easy problem. Okay? But I think it's valuable to do this shear and moment diagram construction both now, because on your homework, the homework's hard, okay? And so I think it's valuable to go through this exercise. Even though this exercise will not directly result in m of x functions, like, what do we know about the m of x function for this beam after this exercise? We know there's only one parabola that fully defines the moment diagram. We know it's a parabola. The x squared term in that parabola, should it be positive or negative?
Negative.
Negative. Why negative? Opening downward. So just with this graphical construction, we learn a lot of data about that equation. So that when we start deriving it, it makes sense. Does that make, everybody okay with that? Okay. So with that being said, now what we're going to do is we're going to cut a section. And I'll just put the section cut right here. Section 1-1. Now, one thing that I did sort of leave off of my initial diagram that I'm going to now start to be more explicit in placing is I'm going to do this. Okay? I'm going to place a coordinate system. So treating this like it was an XY graph. So we'll say the origin is A, so the x-axis goes like this, and the y-axis goes up. Okay? Now, up until now, what I would say is looking left or looking right. Okay? I'm going to state this a little differently. What I'm going to do is I'm going to say section 1-1 towards the origin. And I'm going to give you a piece of advice on your homework. Always look towards the origin. I didn't say always look left or always look right. That's not what I said. I said always look towards the origin. Okay? Trust me. And we will discuss this on Monday, but trust me, the algebra, a lot easier when you look towards the origin. A lot easier. Okay? And you'll see why. By the way, statically, it doesn't matter which direction that you look. Like if you cut a section, it doesn't matter if you look this way or this way. You'll get the same response. You'll get the same equation, but you'll do it a lot more easily looking towards the origin. Okay? So there's my section cut. This is 1.2 kips per foot. Let me lower that just a tad bit so I got some room. Okay. I have my shear, my moment. I'm not going to care about the shear. I just put it there just for the diagram to be complete. And then what do I do? Keep in mind this distance is x, right? Okay. What do? I take that distributed load, I collapse it. How much is the point load going to be?
1.2x.
And a moment arm of
X over 2.
x over 2. Okay. So let's see what we can come up with. So what do I have? 18, how do I handle this? 18. 18 times what?
X.
On left or right? Okay, 18x. What about the 1.2x? It's 1.2x times x over 2, and then m. So I get 18x equals m plus what? 0.6x squared. So I get m is 18x minus 0.6x squared, valid from 0 to 30. Does that make sense? So Does that look the way that we thought it was going to look? Is that a parabola? Does it open downward? Negative x squared term? A single parabola. And if we graph it in Excel, we'll see it works. Sound good? Okay. So now, what we're going to do, all right, does everybody have all this? Everybody have everything here? Any questions on it? Yes?
So you had 18 kips on like going upwards, and then it went over to 18x.
Yeah, because if we're summing moments at the cut, it's 18 times x.
Yeah. So that's just okay. So 18 is just like that's 18 is the only part. It's just what you're multiplying with. X is whatever.
Yes.
Okay.
Because here's the thing. That moment, as we move the section cut away, that moment will increase. But this one will also counteract it. The moment from the load. So, good question. Sound good? Okay. All right. So if that's the case, now what we're going to do, we're going to do all this again. Okay? But what we're going to do is look at the virtual structure. Now this problem asks for 2 deformations. So because it asks for 2 deformations, we're going to have 2 virtual structures. So we're going to have to ultimately do this 3 times. Okay? But let's take it one step at a time. Okay? The first thing we'll do.
Wait, why did you say that we have to do it 3 times?
That's a good question. So the reason we have to do it 3 times is because we're going to be looking at the vertical displacement at B, but we're also going to be looking at the rotation at B. So in order to solve a single problem, we need a real structure and a virtual structure. But we're doing 2 problems. So we use the real results and then 1 virtual result for every one we're about to do. We're going to do the vertical displacement at B. Okay? So what we're going to do is we're going to say, okay, let's do this problem sort of again. So here's this, okay. Let's put our coordinate system on here this time. So y, x. I'm using the same coordinate system as before. Same coordinate system. Okay. We'll put a reaction here, reaction here. We'll call this AY and call it CY. And we'll put A, B, and C. The beam is 30 foot long, so we'll do 10 foot and 20 foot. Okay. Now, how do we do a virtual analysis? How do we do it? We take all of the original loads off the structure and remove them, okay? And we replace them with a single unit load. Where do we put that load? We put it at B. Why do we put it at B? Because that's what we're after. We're after the vertical displacement at B. Sound good? Now, it's a vertical displacement, so we put a vertical load. Do you think that point B on the real structure is going to deflect upwards or downwards? Downwards. So I'm going to put a single unit load like that. And that's our virtual structure. Okay? So what we're going to do is we're going to do this problem the same way that we've done our last problem. Now we can't exploit symmetry on this, so we're going to have to sum moments. Okay? So let's sum moments at A. Okay. So summing moments at A, I'm going to have 1 times 10, and I'm going to have what? CY times 30? Is that right? So 1 times 10 and CY times 30. So 10 feet equals CY times 30 feet. And so that's a third. And so if CY is a third, what's AY going to be? 2/3. So I'll just do it like this. I'll just say, I'll just do that. All right. Hopefully this stuff I can sort of knock out really quickly, that we're not, you know, at this point, this stuff should be pretty simple. Sound good? Okay, so okay. We'll do a shear diagram, and I'll do a little v because this is a virtual shear. So tell me what to do. I start at 0, then what? There we go. From A to B? Nothing. Then suddenly drop down to? We get that, right? Then we do some integration, right? 2/3 times 10 is 20/3. This is going to be negative 20/3, right? So we'll say so our moment diagram I get that. Yes.
And you don't like absolutely have to do the shear moment diagrams for this. It just lets you go in the right direction.
You are 100% correct. But I'm going to show you why for virtual structures, there is one heck of a shortcut.
Okay.
One heck of a shortcut. Okay. I want you to recognize two things. Well, first off, what does our moment diagram look like? It's linear, right? There are two linear functions, right? So what I'm going to do is I'm going to say we're going to have an M1 equals something, right? And it's going to be valid from 0 to 10. And then I'm going to have an M2 which equals something valid from 10 to 30. Would we all agree with that? Okay. So these are lines, right? Okay, so there are two things I want you to recognize. First thing I want you to recognize is what is the slope of this line and this line? What about this line over here? What's the slope of this line? Negative 1/3. What's the slope of this line? 2/3. 2/3. Okay, so okay. So that's the first thing I want you to recognize. Second thing that I want you to recognize is that I hope after this, your favorite number is 0, okay? What you were saying just now is that what we're going to ultimately have to do is cut a section, right? That's what you're saying, okay? Here's what I'm saying. Let's look at M1. Let's look at this first line. You're telling me the slope of this line is 2/3. Okay? Now, I told you that this is a graph, right? This is a graph. What are the coordinates of these points? What's the coordinate of this point right here? 0, 0. Okay? What about that point? What's the coordinate?
10, 20 over 3.
And this one is 30, 0, right? Okay, so what you're telling me, so let's take a look at M1. Are you telling me that it is a line with a slope of 2/3 that passes through the point 0, 0? So, what is M1 then? 2/3 x. Notice how I did that without cutting a section. I didn't have to do it, right? Because the virtual moment diagram is just lines. How about this one? Okay, let's look at M2. All right, its slope is -1/3, and it passes through. Now I got 2 points. What did I say my favorite number was?
0.
So why don't I use the one that has a 0, right? Y'all remember this? Remember that? That maybe what I should say is that. I mean, does that work? Notice how I didn't cut a section. No section cuts. No, none of that. It's just a line. So, to go back to your question, you said, this is just to make sure you're on the right track. Yes, but because the functions are linear, I can do this without cutting sections. Sound good? Okay. Now, one thing I will tell you, that if you use a coordinate system that goes the other way, like the coordinate system that goes the other way, change the sign of the slope. So, but other than that, everything works. But we're going to talk about that on Monday. So, okay. So I can go ahead and do a method of virtual work. Okay. Now remind me, let's go through a couple things. So we know that E, was it 4,000?
Yeah.
And this is 6,000. And what's the formula that we're using? The formula that we're using is the deflection is that, right? That's the formula that we're using. And remind me also, what's our unit conversion factor?
17, 28.
Okay. All right. So I'll tell you this is sort of something that I do. Since these problems are very tabular, or sorry, very, very calculator friendly, I tend to do this in a tabular fashion. I said that backwards. So I'm going to do these calculations in a tabular fashion. So let me show you what I'm going to do. Oh. Okay. So the first thing that I'm going to do is I'm going to say range. Okay? And I'm going to say that the range is, we're going to call this AB, BC. Okay? So the reason I'm doing this is ultimately what you're doing is you're trying to integrate across the entire span. Okay? So you have to account for the entire beam. So if the beam was like, so we have a beam that's like A, B, C. If the beam was from A to point G, we'd have to have an AB region, a BC region, a CD region, DE, so on and so forth, right? Some of them we might be able to combine, but as long as we fully envelop the beam, then we're good, okay? Now, the next thing I'm going to do is I'm going to do this. I'm going to do AB, okay? And all that's going to be is that this is valid from 0 to 10, or this is the range of A to B, and this is 10 to 30. Just to sort of have that there, okay? Next thing I'm going to do is I'm going to list my virtual functions. Okay? So my virtual functions, here it's 2/3 x. Here, 10 minus x over 3. Okay? The next thing I'm going to do is I'm going to say, okay, let's list my real moment function. Now, just so we're all saying, paying attention, what goes in these two slots? The same thing. Because this function is valid from 0 to 30. So if it's valid from 0 to 30, it's valid from 0 to 10, and it's valid from 10 to 30. So I actually list the same thing twice. Okay? So if I have my virtual function and I have my real function, keep in mind for these problems that EI is a constant. We can factor that out. So really what I can have is just a listing from A to B of that, right? So my first integral is going to be an integral from 0 to 10 of M1. We'll call it M delta 1. Maybe we'll do that. We'll call this, we'll get specific. We'll call that delta 1 and delta 2. Since we're going to have a theta 1 and a theta 2 here in a minute. Maybe I'm getting a little too notation heavy, but M delta 1 M dx, and this is going to be from 10 to 30. Okay? So just to sort of make the point, I mean, what I'm talking about is I'm sort of saying, okay, let's, you know, if we're, maybe we'll call this integral 1. So like down here, integral 1 is the integral from 0 to 10 of 2/3 x 18x minus 0.6x squared. Okay. Now, I told you a long time ago that, or not a long time ago, I told you this last time, that we're going to get to a point where instead of me evaluating this, I'm just going to sort of give you the answer. I mean, let me ask you a question. Do you all want to go through this, or can I trust you all that you can do this on your own? Is everybody okay with doing this on your own? Okay. So I'll go ahead and tell you that when it's all said and done, this comes out to be 3,000. And the second one comes out to be 8,000. So I'm gonna erase all this. Okay. So if I sum these up, I get 11,000. So how do I evaluate the deflection at B? So the deflection at B is just going to be the following. It's going to be 1728 over EI times the sum of my integrals, which is going to be 1728 times 11,000 over 4,000 times 6,000. And make that a little shorter. When you chug that out, you get 0.792, or that. And probably the only thing I'm really skipping is this integration. But if you have a Casio FX115 ES Plus or similar scientific calculator, you can literally just plug it in. And even if you don't and you want to do it by hand, I've got to believe that this is an integral that you can do by hand, right? Even this one might be a little bit more complicated, but all you have to do is just FOIL it. FOIL it, integrate each term, plug in 30 minus plug in 10. It's not hard. I know you all can do it. But this is about the most difficult type of integration that we can do in here, stuff that a calculator will just do for you. Okay? Does that make sense? Okay. So if that makes sense, can I go ahead and try and knock out the rotation at B? So we're going to have a rotation at B. Okay. Okay. So for the rotation at B, what we're going to have is we're going to have, again, same type structure, coordinate system. We're going to have reactions here. We're going to have coordinates. And this is A, B, C. Okay. Now, for the rotation evaluation, we don't place a unit force, we place a unit moment, okay? So what I'm going to do is I'm going to place a moment right here that looks like that, okay? And if you're wondering, so I think the structure is going to deform something like that. So here's what the structure did look like. Here's what it now looks like. And so we're rotating like that. So that's why the moment goes that way. Okay? So how do we do our reactions? We sum moments at A. Okay. So what do we have? We have 1 and then something times 30, right? So we'll say that CY goes like that. 1 equals CY times 30, or CY is 1 over 30. Okay? So by the way, if CY is 1 over 30 going up, what is AY?
1 over 30.
1 over 30 down, right? Okay. We're not going to finish this problem all the way, but that's actually kind of on purpose because I want to give you maybe a little bit of practice on your own. All right, so by the way, what does the shear diagram look like? And what does it look like if I start at 0?
Down 1 over 30 and all the way to the right.
All the way up. So it's complete. So this beam is actually experiencing a constant shear, a constant negative shear. So what I'm going to do from an area perspective is I'm going to split this up. I'm going to say negative 1/3, negative 2/3, right? So the total amount of area is negative 1. So what does that concentrated moment do? It's going to shoot us up 1, right? So the moment diagram, which looks very suspiciously like an influence line, which we're going to talk about later. There's some really interesting analogies there, which we'll talk about later. That's going to be our moment diagram. Okay? And so that we're aware, this is a slope of minus 130, a slope also of minus 130. Okay? I'm going to point out that this is 0, 0. This is 30, 0. And given that we are running short on time, what I'm going to do is this. Okay. So what I'm going to say is this. So for practice, I'm going to see if you can arrive at the following conclusions. Okay? Let's see. Okay? And then M2 is, let's see, so what are the coordinates of that point 2? So, oh, sorry. It should be that 1 minus x over 30. And I believe if I did everything correctly in my calculations, I will check this. This is what we get. By the way, keep in mind that and that's still true. Now I'll tell you that I'm sure that some of you, oh, I didn't mean to do that. Oh well. Are like, Dr. Mike said that's for practice. That is not for grade. I don't have time for that. I'm sure some of you are thinking that, and I get it, okay? But I will tell you that going through the process of practicing this, it will make homework 6-2 easier. Here's some honest advice for everybody in this room. For homework 6-2, between now and Monday, I would do the graphical construction of all the shear and moment diagrams. I would not get worked up about the algebra or the calculus, but the pictures for the real structure and for the virtual structure, I would do those. I really would, okay? It will make Monday through Wednesday a lot less painful, okay? Trust me on that. Monday, I'm gonna make your life a lot easier on homework 6-2. But for now, I want you to digest this. I will see you all on Monday. Have a wonderful weekend, everybody.